Hello and welcome to ACSC Academy. This is the part 3 of the topic quadratic equation from our NIMSET series. In the last part, we have already learnt about the remainder theorem, and in this part, we'll be having a look at what different types of problems are expected from the topic. We'll be solving a number of examples from that. So let's begin. And now here we have these two polynomials, p of x and g of x. We have to find out the remainder that will be obtained when we divide the p of x with g of x. We have already seen two different methods of doing so. The first one is using the traditional division. We place p of x over here, g is there, then we perform the traditional division and get some quotient and remainder at the end. And the second method that we saw was using the remainder theorem. Both of these can be used for finding out the remainder for division of two polynomials, but we do not know if both the methods are applicable for solving the same problem and whether it will always give us the same results. So let us take this particular example and apply both the methods on it, and then let us analyze what are the outputs that we get. So going with the first one, that is using traditional division, we will be dividing the two polynomials as it is. So let us write that 2x raised to 6 minus x raised to 5, 11x raised to 4 plus 18x cube minus 26x squared plus 23x minus 3. So this is a huge degree 6 polynomial that has to be divided with a cubic polynomial. So this division is going to be really lengthy and time consuming as well, but just for learning purpose, let us analyze it. So here the foremost term, the one which determines the degree of that polynomial, that is 2x raised to 6, which we'll be dividing with the first term in the g of x, that is x cube. That will give 2x cube. So we have the same over here. Now this 2x cube will be multiplied with both these terms, minus 7x and plus 6. When multiplied with minus 7x, that will give minus 14x raised to 4. And with 6, it will give plus of 12x cube. So now let us subtract. The signs will be changed. This becomes plus, this becomes minus. These are gone. So get minus x raised to 5 plus 3x raised to 4 plus 6x cube. And now we can bring the remaining terms all together or one at a time. Does not matter. We are bringing all of them together. So now in the next iteration, we have this minus of x raised to 5. So that when divided will give minus of x squared as the quotient. So we get that. Then minus x squared with minus 7x, that will give plus of 7x cube. And with 6 it will give minus 6x squared. So again we subtract the terms together. And this one is gone. So we get 3x raised to 4. Here the signs are changed. So this becomes minus 7 plus 6, that is minus x cube. Then here it is minus 26 and plus 6, which is minus 20x squared plus 23x minus of 3. So now going for the next iteration, that will give us plus 3x as the quotient. So get this 3x raised to 4. That when multiplied with 7x will give minus of 7 thrice, means 21x squared. And with 6 it will be plus of 18x. Again when we subtract them, this term is gone. We get minus x cube. Then this is plus 21 and minus 20, so plus x squared. And here we have plus 23 and minus 18, which means plus of 5x minus 3. Now the last iteration will give minus 1 minus x cube over here plus 7x and minus 6. So now we will be getting the remainder, that is x squared. Here the sign will be changed. plus 5 and minus 7. So it will be minus 2x, and here plus 6 minus 3. So we get plus 3. Hence we got the remainder as x squared minus 2x plus 3. And as we can see, the g of x was a cubic polynomial, and we know the degree of remainder is strictly less than that. So we have got a quadratic polynomial in this case. So using the method 1, we got this particular remainder x squared minus 2x plus 3 as the remainder. And now we will be verifying the same using the remainder theorem as well, and then we'll be analyzing the results. So let's move on to that. This particular expression is at the heart of the remainder theorem. What it says is that we can express the given polynomial p of x as the product of q of x, which is some quotient which we are not actually aware of. This g of x is already given to us, and to this we add the remainder. This is unknown for this case, and that is what we need to find out. And how do we get this? The same as we have dividend equal to divisor into quotient plus remainder in the general division. So that is how we get the idea of the remainder theorem. We have already seen the derivation. Now using this, we will be trying to find out the remainder for the same case. We have been given p of x and g of x, and we have already calculated the remainder from the previous case using the traditional method, and there the remainder had turned out to be x squared minus 2x plus 3. So we'll be trying to verify that using the remainder theorem now. So for that, as we remember from the part 2, what do we try to do is we try to eliminate this particular product term. And how do we do that? By substituting those values of x which will make it 0. And how do we do that? We do not know what q of x is. That is unknown to us, but we do know g of x. So we will substitute those values of x which will make g of x as 0, which means we will be using the roots of g of x. And we already have this g of x given to us. So we'll be finding out its root first by factorizing it. Then we will substituting those roots over here that will vanish this particular product term. And then we will be able to relate p of x with r of x. So that is how in a simple way we can reach at the remainder. But it all depends upon whether or not we are able to find the roots of g of x. Now in this case, it is a cubic polynomial. So we can try to factorize it using different ways. It is possible that we are not able to factorize it. It will stay this cubic itself. Or it is possible that we can factorize into one linear and one quadratic polynomial. Or it is possible that we get all three as the linears. So any one of the three cases is possible, and depending upon which case it is will determine whether or not we can solve this problem or we can find out this remainder using the remainder theorem or not. So let us go ahead and try to solve this particular question. Here we have g of x as x cubed minus 7x plus 6. So in order to factorize it, what we will do, just by looking at this given expression, we can see that g of x equal to 0. This is how we find the roots of it, right? So if we put g of x equal to 0, then for this equation, if we substitute x equal to 1, then we can see that it becomes 1 minus 7 plus 6, which is 0, which means 1 is the root of g of x. So we have already found one root, that is 1, which means a linear term. So we have got one factor of g of x. Now what will be left out? In general, how do we find out or how do we factorize a cubic polynomial? First, we use the hit and try method, which means we try to substitute different values of x, whether it be 0, 1, minus 1, like that. And as soon as we find one of the roots of it, then what do we do is we use that root and then we divide it this way. We know that x minus 1 is the root, which means it will divide g of x. X cubed minus 7x plus 6. One root is already known, so we will divide using that x minus root value, which means, let us say alpha turns out to be the root of g of x. And what does that imply? X minus alpha will be divisible by it. So we will actually divide the given polynomial with x minus alpha value, and then whatever quotient that we obtain, that will be its further factorization. Definitely the remainder obtained would be 0 because it completely divided, and that we already know. So let us perform this division over here. It will be x squared, x cube minus x squared. So we get this is cancelled, minus x squared minus 7x plus 6. Again minus x, so minus x squared plus x. So now here we get the signs will change. This will become minus 8x plus of 6, but the remainder should not be left out, which means we made some mistake. Let us cross check it again. It was x cube, so we took x squared, so x cube over here, then that multiplied with minus 1 gave us minus x squared. Okay, here we forgot to change the sign, it will be plus of x squared. Okay, let us do that again from this point onwards. It will be x cube, and then this x squared multiplied with minus 1 will give us minus of x squared. So now the sign will change and it will come down as plus of x squared. These will be as it is, minus 7x plus 6. So now in the next time this will be plus of x over here. So x squared, and we get x and minus 1, so that will give us minus x. Now over here again this is cancelled out, this becomes plus, so minus 6x plus 6. So minus 6 over there, and we get minus 6x plus 6, and it is gone. So the next term that we got is x squared plus x minus 6, which means we have factorized it into a linear and a quadratic. But now is it possible to further express this quadratic as a product of two linears, or can we find out the roots of this polynomial, the quadratic, as well? Now as we can see, we have this x squared plus x minus 6. So if we substitute x equal to 2, that becomes 4 plus 2 minus 6, which is 0. So we can substitute x equal to 2, and that is one of the factors of it. So we will write it as x minus 1, x minus 2, and then what will be the third term when we divide this particular quadratic with x minus 2? This can be factorized into x minus 2 and x plus 3. As you can see, we need the sum to be plus 1 and product to be minus 6. So the terms will be x minus 2 and x plus 3. So this is our factorized g of x. So now we will substitute that over here and use this particular expression for the evaluation of r of x using the remainder theorem. So let us see how that can be done. So now here we have written this in the form of p of x equal to product of q of x into g of x. This is our g of x written in terms of its factors. We had already found 3 factors of this g of x, which was a cubic equation given to us. And then this is our r of x, the remainder that we have assumed. How did we come to this? G of x in our case was a cubic polynomial. It was having a degree 3. So we assumed the remainder to be a general polynomial of degree 2, because we know that its degree is strictly less than that of g of x. So we assumed r of x to be a general polynomial of degree 2, that is ax squared plus bx plus c. So now we have written this p of x in terms of q of x, g of x and r of x. So now we will apply remainder theorem onto this to find out the values of the constants a, b and c, so that when we substitute them back over here, we will get the actual remainder. This is the theoretical remainder, or the one which we have assumed. It is not the correct remainder. We need to find out the values of a, b and c. So for that, what will we do? We will one by one substitute some values of x, which will help us form the simultaneous equation, and after solving them we can get the values of these constants a, b and c. Now what are those values of x which we are going to substitute? Those values are found using these factors. These are the factors of g of x. We will be substituting those values which will help us vanish this entire product term together. For example, the first term, as you can see, it is x minus 1. So if you substitute x equal to 1, then this first term will be gone, and along with it, this entire product term will also be eliminated. Similarly, if we substitute x equal to 2, then this second factor will become 0, and as a result of that, entire product term will be gone. Similarly, if we substitute x as minus 3, then the third factor will become 0, and as a result of that, again entire thing will be gone. And after that, we will be able to relate p of x with r of x. That will help us find out the actual values by arriving at the simultaneous equations. So let us see how that can be done. One by one, we will be substituting the values of x and getting the simultaneous equations. So let us begin with substituting x equal to 1. So here we will be getting p of 1 when we take x as 1 equal to. Now here, as you can see, if I take x as 1, this will become 0. So the entire thing is 0 now. And we have just this remainder left. There, when I substitute x as 1, I will simply get a plus b plus c. Now next, substituting x as 2, I will get p of 2 equal to, this second factor becomes 0, and as a result, entire term is gone. Coming to remainder, it will be 4a plus 2b plus c. Now, the third factor, it is having a root as minus 3. So when I substitute x equal to minus 3, this will be gone. It will become 0. Entire term is eliminated. I get p of minus 3 as, from this remainder, 9a minus 3b plus c. So now we have got these three equations, but the values are still not clear. They are in terms of p of something. We do not know what are the values of these. So now we will substitute these terms in our polynomial equation, and we will find out the values of these p of 1, p of 2, and p of minus 3. How do we do that? We already have been given this equation to us. So we will simply substitute x equal to 1 in it to find out the value of p of 1. And how will we do that? It will simply be 2 minus 1 minus 11 plus 18. That way you can easily calculate that. So when you do so, we get the value of p of 1 as 2. And for p of 2, we get the value as 3. Similarly, for p of minus 3, we get the value 18. So now, here we will substitute their results, 2, 3, and 18. So these are our simultaneous equations. We have got three equations in three variables. Now we will solve for a, b, and c. We will find out the values of them, and then we will substitute those values back in the assumed remainder to get the real remainder. Let us see how do we solve that. We are having those equations. Let us number them as 1, 2, and 3. So now if we subtract equation 2 and 1 this way, then this c will be eliminated because it is having the same coefficient in both of them. So this 2 minus 1 gives us 4a minus a, 3a, 2b minus b, that is b. C is gone, c minus c 0. On the right hand side, 3 minus 2, 1. So this is what we get. One variable is eliminated. Now in the same way, if we subtract 1 from 3 as well, then also c will be gone because again it's having the same coefficient. So 3 minus 1 gives us 9a minus a, which is 8a, minus 3b minus b, so minus 4b, equal to 18 minus 2, 16. So now let us call these new equations as 4 and 5. So we have to solve these two and find out the values of a and b. So how do we do that? We can multiply this equation 4 by 4, then b's coefficient will become same. So that will be 12a plus 4b equal to 4. And equation 5 as it is, 8a minus 4b equal to 60. We will add them. 12 plus 8, 20a gone, equal to 20. So now we have got the value of a equal to 1 from here. And we will substitute this value of a in equation 4 over here to get 3 plus b equal to 1, which means the value of b turns out to be minus 2. And in the same way, we will be getting the value of c by substituting both a and b in equation 1. So we get 1 minus 2 plus c equal to 2, which means c minus 1 equal to 2. So we get c equal to 3. So we have got all the three, a, b and c. A is 1, b is minus 2 and c is 3. So this is our remainder, assumed remainder, in which we will substitute the result that we got here, the values of a, b and c, to get x squared minus 2x plus 3. This is our real remainder. And as you remember, using the method 1, which means using the traditional division also, we had got the same remainder. And now we have cross-checked that with method 2, that is remainder theorem as well, that we are getting the same result. So the same problem, we have solved it using two different methods and we have got the same results, of course. So definitely, as you can see, the method 2 was easier in this case. It did not take so much time compared to method 1, which was very lengthy because the given polynomial was large. It was having degree 6. So in such cases, when we can easily factorize g of x, in such cases, we should definitely go for this particular method of remainder theorem for finding out the remainder. And if it is not possible to easily factorize the polynomial g of x, then we might need to go with the traditional method itself for finding out the remainder. We will have a look at such an example. So this is one such example where the remainder theorem may not be applicable. As you can see, this is our g of x. Let us try to factorize this. As we can see, if we substitute x equal to 1, then we get it as 1 minus 1 plus 1 and minus 1, which is 0, which means x minus 1 will be one of its factors. Let us divide it with x minus 1 to try to find out the other factors of g of x. X cubed minus x squared plus x minus 1. Let us perform this division. This is x squared, x cubed minus x squared, both are gone. So we get x minus 1 simply, 1 times x minus 1 and 0, which means g of x can be factorized as x minus 1 and x squared plus 1. So this is how we could factorize g of x. Now as you can see, g of x is having a degree 3, which means the remainder that we will be assuming, that will be a general polynomial of degree 2, which means ax squared plus bx plus c type of remainder we will be assuming. It will be having 3 constants a, b and c. But as you can see over here, in the factors of g of x, what are the roots? X equal to 1 is the only real root that we have over here. The second factor, which is x squared plus 1, it is a quadratic, which does not have any real root. So when you will do it this way, when you will write p of x equal to q of x into g of x, in place of g of x you will write its factors, x minus 1 x squared plus 1 plus r of x. And here you will be substituting x as 1. So we will get p of 1 equal to r of 1, which means a plus b plus c equal to 1. That is the first simultaneous equation that we will be getting. This is p of 1. So that is the only equation that we can get. There is no other value that we can substitute for eliminating this term over here, because the second factor is not having any real root. So here we will simply be able to arrive at a relation that a plus b plus c is equal to p of 1, which is, what is p of 1? 1 plus 1 minus 1 plus 3 minus 3, which means 1 itself. So you can only say that a plus b plus c equal to 1. You cannot find the individual values in this case. Only reason being that g of x does not have proper factors. And by proper factors, what do we mean? That we should be able to arrive at 3 simultaneous equations. Then only we will be able to eliminate these 3 unknown constants a, b and c, which means g of x must have 3 roots, 3 real roots, if we want to eliminate these 3 constants of r of x. Otherwise it will not be possible for us to apply the remainder theorem in this case for finding out the remainder. So how do we come to know whether or not to apply the remainder theorem? Look at g of x. If you can easily factorize it into all the linear equations, then well and good. Go ahead with the remainder theorem. And if not, if you're not getting all the real roots of it, which are necessary for removing these constants in the remainder, then do not go for this method. Go with the traditional division method in order to find out the remainder. So this was one such example. There would be many more in which this is not always applicable. We'll have a look at another example. This question is saying that we have a polynomial p of x that when divided by x minus 1, x minus 2 and x minus 3 respectively, then it leaves the remainders 10, 20 and 30 respectively, which means if you divide p of x with x minus 1, then the remainder will be 10. With x minus 2, the remainder will be 20, and with x minus 3, the remainder will be 30 respectively. What they are asking us? Find the remainder when p of x is divided by the product of all the three, x minus 1, x minus 2, x minus 3. So that is our question. When we were dividing them individually, then the remainders were 10, 20 and 30. So now when we divide them with the product of all the three, what will be the remainder? Will it be 0, or will it be the sum of the three, that is 60, or will it be the product of the three, that is 600, 6000? It will be the product of all the three, or none of these. These are the 4 options that we have. So how should we approach this problem? First of all, let us see what can we infer from this. They are saying that p of x divided by x minus 1 leaves the remainder as 10, which means this is what we have been learning from the last 2 parts in the remainder theorem, that if you divide p of x with something and that leaves some remainder, so that simply implies that this p of 1, this was something as x minus alpha. So when we substitute alpha itself, which means p of 1, that will have the value as 10. P of 1 will have the value 10. Then only when you divide it with x minus 1 will leave the remainder as 10. In the same way, we can say p of 2 equal to 20. Only then when you divide it with x minus 2, remainder will be 20. And in the same way, p of 3 will be 30. So this is what we can derive from the given information. Now this entire thing, the product of all the three, is our g of x. We do not know what p of x is. We have to divide this with g of x and find out the remainder. Let us see how this can be done. Got p of 1 equal to 10, p of 2 equal to 20, p of 3 equal to 30, and we have the given equation polynomial g of x as x minus 1, x minus 2, and x minus 3. So now, as we can see, g of x is a cubic polynomial. It's having a third degree, so we will again assume the remainder as a general second degree polynomial, that is a quadratic ax squared plus bx plus c. And now we will apply the remainder theorem in the usual way as we have been doing. So that will give p of x equal to q of x times of g of x. This is x minus 2, x minus 3 plus r of x, that is ax squared plus bx plus c. So now we will do the same thing which we have been doing. For these three factors, we will one by one make them 0 by putting their roots as the value of x, so that this entire product term is gone. So first we will take x as 1, because of which this factor will become 0, and we will get p of 1 as, from this remainder, a plus b plus c. We will get p of 2 as, the second factor will be 0. So now putting 2 in the remainder part, it will be 4a plus 2b plus c, and p of 3 will be, the third factor will become 0 now. So 9a plus 3b plus c. And at this point, how do we proceed in the usual way for solving such problems? We substitute the same values of x, that is 1, 2, and 3, in the given polynomial p of x. But here we do not know what is the polynomial p of x. That has not been given to us. Instead, we have directly been given the values of p of 1, p of 2, and p of 3. So we do not need to substitute them and then calculate. That is already present. So we will directly write that over here. 10, 20, and 30. So now we have got these three equations in three variables. So we will now be solving them and finding out the values of a, b, and c. Let us call them as equation 1, 2, and 3. If we do 2 minus 1, then we will get 4a minus a, that is 3a, plus b equal to 10. And in the same way, if we do equation 3 minus 1, then we will get 9a minus a, that is 8a, plus 3b minus b, 2b, equal to 20. So now here, let us call this as 4 and 5. Now what we'll be doing is 5 minus 2 times of 4, because we can then eliminate this b variable. So equation 5, 8a plus 2b equal to 20, and 2 times of equation 4, 6a, plus 2b equal to 20. So here we do not get any result. We are left with 0 equal to 0. That has become an identity. And when do we encounter such situations? When any one of them would be 0. Either a will be 0 or b will be 0. Which of them will be taken as 0 now? A has been eliminated. Here we actually got 2a. That's what 8a minus 6, that is 2a, equal to 0. So from here we get a equal to 0. And when we substitute this value of a in, let us say, in equation 4, then we will get b equal to 10 simply, because a is 0. So we got b as 10. And now putting both a and b in any one of the three equations, let us say in equation 1, if we substitute that, then we will get 0 plus 10 plus c equal to 10, which means c is also 0. Let us see if these three values are applicable, if they satisfy the other two equations as well. In equation 2, if we substitute them, then we will get 0 plus 20 plus 0, that is 20. So that is satisfied. In the last one, that will be 0 plus 30 plus 0. It is also satisfied, which means these three values are true. And now we simply have to substitute them back in our assumed remainder. So we will get r of x as 0x squared plus 10x plus 0, which means simply 10x. This will be the remainder. So for our p of x that is unknown to us, when that p of x is divided by this particular g of x, then the remainder that we will be getting is simply 10x. This is what we had to find out. So now this was one of the favorite problems that is asked from this particular topic, and we have seen a number of examples from this remainder theorem topic, and in the next part we will be moving on to the factor theorem.